geometry, because we probably all know about integers and homology. So a context structure is going to be a maximally non-integrable hyperplane distribution on an odd-dimensional manifold. And for those of you that maybe studied differential geometry a long time ago, what that means is that locally, we're never going to be able to find a point where the hyperplane distribution is given by the tangent planes of a 2n minus 2 dimensional submanifold. So it's going to look something kind of crazy like this. And it would be kind of awkward as a contact geometer if I had to carry all these planes around with me everywhere. And you would want a better way to check that something is maximally non-integrable. And luckily, we can do this with contact forms. So the kernel of a one form is going to be a contact structure whenever alpha wedge d alpha to the n minus 1 is a volume form. And this is equivalent to d alpha restricted to C being non-degenerate. And so this is the sort of same example in R3. And the favorite contact form in R3 is dz minus y dx. And you might not be able to generate these pictures in your head right away, but you can at least check that alpha wedge d alpha is dx dy dz, which we all hopefully agree is a volume form on R3. Okay. So in contact geometry, something that we're going to be interested in is the Rabe vector field, and it's kind of analogous to the Hamiltonian vector field from symplectic geometry. So in symplectic geometry, you choose a Hamiltonian, and then that gives you your Hamiltonian vector field. In contact geometry, all we care about was the hyperplane distribution, and many different choices of contact forms are going to give the same contact distribution. And so the Rabe vector field is going to depend on the choice of this contact form. And it's determined uniquely by these two equations. Alpha of r is 1, so that's a kind of normalization. And then we want the contraction of r with the alpha to be 0. So that tells us that the flow of the Rabe vector field is going to be transverse to my hyperplanes. And one nice example is S3. So the standard contact form on S3 is this lovely formula. And it turns out that the Rabe vector field is generated by the derivative of the Hopf fibers. And so the Rabe orbits are going to correspond to the Hopf fibers. And Patrick Massot has a nice illustration where the fuchsia planes are supposed to be the contact structure along some line, and you've got the Rabe flow passing transversely through them. And then Niles Johnson did a really nice job animating the Hopf vibration. So if this was a 5-minute talk, 3 minutes of it would be spent with this beautiful video. So the next question is, what kinds of invariance do we have of contact manifolds? So in symplectic geometry, everything locally looks like R2n, and in contact geometry, everything is going to locally look like R2n plus 1, and there's a standard contact form we can pick. So that forces us to look for global invariance. And the motivation for a lot of this comes from the Weinstein conjecture, which is that any closed-oriented contact manifold is always going to have at least one closed orbit associated to its Rabe vector field. So this was based on work that Rabinowitz did in the 1970s, and he proved that star-shaped hypersurfaces had to admit at least one periodic orbit. And Alan Weinstein, who's a symplectic geometer at Berkeley, realized that this notion of star-shaped could be generalized to the notion of a contact structure. And then it took Taubes a while, and there were some other contributions by some people in this room. But in Dimension 3, Taubes proved this in 2007. And then another sort of related conjecture is that the tight contact 3 sphere admits either 2 or infinitely many simple Rabe orbits. So we can kind of ignore what tight means for now because it's a 15-minute talk. And the infinitely many simple Rabe orbits just means that we're in the case where we're the standard S3 and we have the Hopf vibration. There's obviously infinitely many Hopf fibers, so that's where the Rabe orbits would be coming from. And to be in the case where we just have 2 simple Rabe orbits would be if you were working with an irrational ellipsoid. And there has been some progress towards this conjecture. So Cristofaro, Gardner, and Hutchings have proved there had to be at least 2 simple Rabe orbits, so that's a step in the right direction. And then Hofer, Vysotsky, and Zander proved the conjecture for the dynamically convex 3 sphere. And then another conjecture by Hutchings and Taubes is that the only contact 3 manifolds that admit exactly 2 simple Rabe orbits have to be either a sphere or a lens space. Otherwise, there are always infinitely many simple periodic orbits. So that's pretty remarkable because it's telling us that the Rabe dynamics really tell us something strong about the topology of our manifolds, and pretty much all oriented closed 3 manifolds admit contact structures. So if you could prove this conjecture, well, you'd probably have a tenured position somewhere nice. Okay. So I haven't proven any of these theorems, but my work is on developing homology theories that are invariants of the contact structure. So in Morse theory, you can do this with smooth manifolds. So we want to kind of try to mimic this procedure in Morse theory, but it's not really going to go so awesomely. So we're going to have a closed contact manifold, and alpha is a non-degenerate contact form, which you can kind of think of as the Morse condition. So we want an isolated number of critical points. And then we're going to do Morse theory on this fake action functional, where we're going to integrate alpha along loops on the manifold. And then it kind of looks like Morse theory because all of the critical points of this action functional are just going to be closed Rabe orbits. But then when I define the differential, it's not going to look like gradient flow lines, so it stops looking like Morse theory. But that's kind of the first motivation for this. The gradient on the orbits is going to be given by something called the Conley-Zander index. It's a half integer you can associate to arcs of symplectic matrices. We can get these arcs by linearizing the Rabe flow. And then the chain complex is a little bit annoying to explain. It's going to be a vector space over Q generated by the set of good Rabe orbits, and that means that we take all of the closed Rabe orbits and we throw out the bad ones. And I don't really want to define what bad Rabe orbits are, but you can figure them out looking at the eigenvalues of their linearized return map. Okay, so in order to define a differential, we're not going to be able to use gradient flow lines, but we are going to be able to use something called finite energy pseudo-holomorphic cylinders. And these are going to basically be maps from cylinders into the symplectization of the contact manifold. So we just cross the contact manifold with R, and then we want them to satisfy the Cauchy-Riemann equations. Our J here on the symplectization doesn't need to be integrable, so that's why they're called pseudo-holomorphic. And then we want them to be asymptotic to periodic Rabe orbits. So as we go off in the plus infinity direction of the symplectization, as we go off to the plus infinity direction of the cylinder, we want to go to the plus infinity and minus infinity direction of the symplectization. And if we project the plus infinity part of the cylinder to the manifold part, we want to be limiting on closed Rabe orbits. And then because we're going to be counting things, we want to do this up to reparameterization. And we have some natural actions by R and S1 that we need to mod out by. And the differential is going to be a weighted count of these pseudo-holomorphic cylinders. And then we want to hope that this is independent of our choices. So Eliashberg, Giventhal, and Hofer conjectured that this should be true. That if you assumed it's a conjectum. So it's when it takes you 100 pages to write down a conjecture. And when people you want to assume a minimal amount of things, and then the claim is that this procedure gives you a chain complex, and the homology is independent of alpha and J, and Helmut's polyfolds will upgrade this to be a real theorem soon. Okay, so what is the problem? So in Hamiltonian Floer theory, we're just looking at time 1 periodic orbits. So we don't have multiply covered curves to deal with, but in the case of contact homology, we do. And so that means we're going to have a hard time establishing transversality, which just means that we want to prove our linearized D-bar operator is surjective. And if we don't have transversality, then we don't know that this moduli space is a manifold, so it could just be some nasty set. And if it's some nasty set, it could have non-positive virtual dimension, which means that we have really horrible compactness issues, because in Morse theory, you have an index 2 flow line. To prove D squared is 0, you want to prove that the compactification, you just have to include once broken cylinders, and to add to 2 with positive numbers is just 1 plus 1. But if stuff has non-positive virtual dimension, then you can add to 2 in a very interesting way. So then you can't prove that D squared is 0. Okay, so luckily in dimension 3, there are some really nice facts about the Conley-Zander index and automatic transversality. And if you assume some relatively strong things about the types of contact forms you can consider, then you can get D squared is 0 and get invariance. and under the choice of almost complex structure and class of contact forms you're considering. Luckily, you don't have to assume such strong things that this theorem is about the empty set, so we're good. So in particular, this theorem holds for pre-quantization spaces and other circle bundles over orbifolds. But, you know, this is not like the best thing, and, you know, you don't want to be stuck in 2013, so you do some more index calculations, you learn some intersection theory, you team up with another mathematician, and then you prove that the remaining obstruction to d squared being 0 can be excluded in dimension 3. So it turns out that this is the sole sort of remaining compactness index issue. It turns out that our theorem is going to work for dynamically convex contact forms, and this basically just means that we assume something about the first Chern class, so it makes sense to say that every contractible Rabe orbit should satisfy Conley-Zander index being greater than or equal to 3. And an important class of dynamically convex contact forms are going to be convex hypersurfaces in R4 that are transverse to the radial vector field. So that's obviously a non-empty set of dynamically convex contact manifolds. And then the theorem that Hutchings and I proved is that for dynamically convex contact 3 manifolds, we can prove that d squared is 0. But of course, we still would like to prove something about invariance. So then we have to do a lot of stuff. So we come up with some non-equivariant versions of contact homology, and we do this using domain-dependent almost complex structures. We use obstruction bundle gluing, and then we wave our magic S1 equivariant wands, and we get an integral lift of contact homology, which is defined over Z, and we can also recover the old formulation of contact homology by tensoring our theory with Q. And we get invariance this way, so that's awesome. Okay. And one thing that's nice about the theory we would develop, this integral lift of contact homology, is that it sees a lot more about the dynamics floating around of Rabe orbits. So there's something pretty standard from dynamical systems called the period doubling bifurcation. And we're going to go from a simple Rabe orbit that's elliptic to a Rabe orbit that's elliptic of twice the period and also a negative hyperbolic orbit. And we do this by perturbing the flow in a neighborhood by some time epsilon flow of a Hamiltonian vector field, which I've drawn in these pictures. And then we're going to rotate by 180 degrees. So the fixed points of this Hamiltonian vector field X, when you rotate by 180 degrees, if you match back up with your fixed point, you're going to end up with a periodic orbit. So at this r equals 0 parameter, we have an elliptic orbit E that corresponds to this center point. And then at time 1, the bifurcation gives us a negative hyperbolic orbit, which is at the origin of figure 3. And then we've got an elliptic orbit E2 of double the period, and that's by connecting the two fixed points in between the two circles on either side of the hyperbolic orbit. So locally, the sort of classical version of contact homology would be generated by good orbits which wind k times around some neighborhood of your Rabe orbit. And for k equals 2, we'll have one generator, which is going to be going around the elliptic orbit twice, and one generator after. And the reason why we only have one generator after is because the negative hyperbolic orbits are going to be bad orbits, so we have to throw out their even multiple covers. And then local integral contact homology is going to see a lot more. In particular, it's going to pick up some Z mod 2 torsion from the likelihood of a good sort of elliptic orbit to become into a negative hyperbolic orbit, which is written down here, but no one can see that. So in particular, with local integral contact homology, you can see that you get the same answer before and after the bifurcation, so that's always good news. And it's sort of nice because dynamically it's saying, look, this possibility of a Rabe orbit to undergo a period doubling bifurcation and turn into a negative hyperbolic guy is going to contribute some Z mod 2 torsion. So future work of mine will sort of investigate more dynamical questions with this sort of more high-powered contact invariant.